My name is Thiago Lima Silva, and I'm going to present the work entitled Data-Driven Gas Lift Optimization Using Automatic Online Well Testing. And this work was done in collaboration with Alexei Pavlov. So before I start explaining what was done in this project, I need to contextualize the application. So in this left plot, here you can see a typical oil production system in offshore. So basically, this system contains platforms, a bunch of pipelines. The wells are in the subsurface, producing to the collectors, which are called manifolds, which then receive the production from the wells and direct the production to the platforms. Here I bring in a schematic of this production system. So you can see that there are several wells producing to manifolds, collectors, which are in the seabed. And the production is directed to the processing facilities. In the processing facilities, the production is split into gas, oil, and water. So the overall objective is to maximize the oil production. But in some of the cases, the production of the wells is not sufficiently high or is not economically viable. So what's done? A portion of the gas is extracted and re-injected into the wells. So then this constitutes what is called gas lift optimization problem, and the main goal is to determine how much of gas, what is the rate of gas that you allocate to each well individually, such that the oil production is maximized and also the constraints in the platform are respected, such as the constraint in the water production. So the current industrial practice is to utilize models, first principle models, to represent the phenomena and the process of the previous production system that I just explained. The only issue with that is that these models are typically inaccurate. And if you want to get more information from the field, usually you need to perform well testings, which usually yield economic losses because you need to stop some wells and you need to reduce the production of some wells, and just these stoppages they can cause high economic losses. So the solution that we propose is an automatic well testing, and I'm going to explain graphically how that works. So basically, if you have a set of wells in your production system, we introduce small excitations, which we call here, we termed here as automatic well testing. So these automatic well testing, these small excitations, are added to the nominal inputs of the wells. And by doing that, we collect measurements of the field, and with this field data, we propose the use of an automatic optimizer, which then performs the automatic adaptations in the inputs, such that we optimize the performance of the system. So in general, the main challenge which is involved in this solution is how to coordinate the automatic well testing in these individual wells such that we don't cause any disturbance to the platform. So the benefits with the proposed method are the following. First, let me show you what happens in the constraint regarding the total water production at the platform. So you can see here that the total water production with the standard methodology without coordination of the well testings, like the automatic well testings, is shown here in this yellow plot. And you can see that there are large variations, and these variations can cause violations. You can see here the total limit of water in red, and you can see that there are violations in the constraint. With our proposal, basically you can see the black plot, and you can see that it satisfies, it honors the constraints at the platform. So if you look now what happens with regards to the objective, you can see that the total oil production, which is the economic objective of the method, if you compare the results with the standard method, which is the one with large variations, and with our method, you can see that we also propose, with our methodology, there are also we don't cause variations in the total objective. And you can see that because of these variations, what would need to be done with the standard methodology you need to decrease the total production such that you don't cause violations. And that can cause economic losses. So with our method, this is not needed because we are able to stay below the total production. So as I told you before, this is only possible because we have a way to coordinate the automatic well testing in the different wells. So I'm just showing that these small automatic well testings are happening in different ways in the different wells. So the total summation of these automatic well testings, they are represented in this right plot. And you can see that with the standard proposal, there are large variations with the blue, in the blue plot. With our method, you can see that in this line close to 0, this is the overall perturbation excitation that our method calls in the platform, which is near 0. So a summary of the results are that we propose a methodology to optimize the gas lift allocation based on automatic well testings. And our methodology relies on the coordination of well testings such that we avoid economic losses and equipment wear. And by employing the methodology that we propose, we allow a safe operation near the optimum without any constraint violations. So the results of this work hindered 2 publications. So the first one is this publication, which appeared in the European Control Conference this year, and the second one is a publication that appeared in the IFAC World Congress also this year. So this project is sponsored by NTNU, and this concludes my presentation. I would like to thank you all for your attention.